I'm going to go through the first load of questions from the set 1 questions, multi-choice. So first of all, this question. First of all, have a look at the axes, and this is a displacement time. You can also have displacement distance graphs. So let's go through each one. Frequency is 500 Hertz. Well, frequency is 1 over time period. And if we do 1 over the time period, which is 4 times 10 to the minus 3, as it's milliseconds, you get 250, not 500. The graph shows this is a transverse wave. Well, first of all, sound is never transverse, it's longitudinal. And there's no way of knowing that from the graph, so no, this is not true. The intensity of the wave will be doubled if the amplitude is increased to 0.4. So currently the amplitude is 0.2, so that would constitute a doubling of the amplitude. A reminder that intensity is proportional to amplitude squared, so it wouldn't double, it would actually quadruple, so that's not true. Last but not least, therefore, must be true, and the way you can prove that is using V equals F lambda. You can find the velocity from the question, 320, and you can find the frequency from your calculation up here, 250, and you'll find that you do get 1.28. First thing to do on this question is to work out the wavelength, using the fact that it's equal to V over F. So if we do 24 divided by 15, we find that the wavelength is 1.6 meters. So, what is the phase difference between 2 points 2 meters apart? Well, 2 meters apart, one whole wavelength is 1.6. Then we're going to go a further 0.4 meters. Now, 0.4 meters, if you divide that by 1.6, corresponds to a quarter of the wavelength. So we're going to go a quarter of the wavelength further, which would be that. So we're comparing this point and this point. Now, you might remember that one whole wavelength corresponds to a whole cycle. And this is asking just in terms of cycles, not in terms of degrees or anything, how far out of phase they are. But we can see here it's going to be a quarter of a cycle because 0.4 meters is a quarter of the wavelength further ahead. If we continue this wave, that would be another whole wavelength. So you can see that up to there corresponds to a quarter. The answer is B. A wave of amplitude A has intensity 3 times 3. What is the intensity of a wave of the same frequency that has an amplitude of 2A? So notice that we're doubling the amplitude. Remember that intensity is proportional to amplitude squared. So if we double the amplitude, we're going to end up with 4 times the intensity. So 4 times 3 is going to give you 12. Your answer is D. And this one relies on you knowing a few kind of randomish facts, some from the first topic when we did estimations. You might remember nucleus. Well, an atom is about 10 to the minus 10 meters. A nucleus is about 10 to the minus 15 meters. You've only got to know this roughly because you'll realise then very quickly that gamma, which has the shortest wavelength, tends to be shorter than 10 to the minus 10, 10 to the minus 11 meters. So this is well and truly in the gamma region. So the answer is A. This one's asking for the phase difference between the two waves. They have the same frequency and the same wavelength, otherwise you wouldn't be able to do this. Basically, we're saying how far apart are they in terms of phase angle. Now, we'll see that conveniently one oscillation here is 360, which it should be, because that's one oscillation, which is 2 pi radians, if it was in radians. And if we look roughly, let's get a rough idea. If we dot down, we see they're about 100 degrees apart. Now, that's not an option. But we don't need to panic in this situation because it could be that this peak should be compared with this peak. Or, remember, every 360 degrees this repeats. So we can do 360 minus 100 gives me 260. So therefore, that's the phase difference, C. So you could say this one is 260 degrees behind that peak there, which is the same as saying it's 100 degrees ahead, but that's just not an option. If it was, we could choose that, but it isn't. A sound wave has a speed of 330 and a frequency of 50. So again, first thing we're going to do is find a wavelength, like we did previously, V over F, which is 330 over 50. So that gives me 6.6 meters. Now they're saying which 2 points are 60 degrees phase difference. Now remember 60 out of a total of 360 degrees for one complete oscillation. If we then times that by the wavelength, we can see what what's the possible answer for this one, which gives us 1.1 meters. So there we are. So 1.1 meters corresponds, because the basic thing about it is a ratio. 1.1 over 6.6 is the same as 60 over 360. Just remember that one complete oscillation is 360 degrees. Though we may have not done interference patterns by the time we watch this, I'll go over this briefly now. Now, the things that are essential, you definitely need the same frequency, and for it to be coherent, they mean the same thing. Coherent means the same frequency. If you don't have a observable interference pattern. They do interfere, but it constantly shifts. You can't see it. Equal amplitude. Now, they don't actually have to have exactly the same amplitude. You might not get real dark spots if they're not the same amplitude, because obviously a wave like that will interfere maybe with a wave like that. But yeah, that is not essential. So that's our answer C. They must overlap obviously to interfere, so that is essential. We've got a CRO here and the time-based setting. Remember, the time-based says what 1 millimeter in this case corresponds to. So 5 times 10 to the minus 6 equals 1 millimeter. Now, the frequency of the wave. Well, let's first of all find the time period of one wave. So we could go from there to there. It's about the same. So it's 1, 2, 3 squares, or 30 millimeters, 3 centimeters. What's this? So if we times that by 5 times 10 to the minus 6, we'll get the time period of this wave. That gives me 1.5 times 10 to the minus 4 seconds. Frequency is 1 over time periods, so we just pop that into that equation, and we get 666 hertz, which is 6.7 kilohertz. Watch out for the trap. Don't just circle it straight away. Wave pulse moves along a stretched string to the right. Which diagram correctly shows the variation with time t of the displacement s of particle p? Now this is p here. Effectively think of it as a ring, and this is kind of like a wire that's moving to the right. So what's it going to do next? The first thing it's going to do is move up for this section. So the first thing we're expecting is it to displace itself upwards. So these two are gone. Then it's going to stay at a constant height. So constant displacement, so we expect it to stay constant distance away from the equilibrium position. Then it's going to drop down and return up, so it's this one here, D. You either know this one or you don't. If you don't, just learn your wavelengths. The answer for this one, 10, is B. Which statement describes a situation where polarization could not occur? So, reminder that longitudinal waves can't be polarized. So the first thing you do is check, is any of these longitudinal? And you'll spot, first of all, sound waves are there, and therefore that cannot occur. Microwaves can be polarized through a metal grid, and light waves, likewise when they're scattered or reflected, are polarized as well. The reflected bit is why we can remove glare with the Polaroid in your sunglasses. Which statement about waves is correct? All electromagnetic waves travel at the same speed in a vacuum, correct, 3 times 10 to the 8. Longitudinal waves can be polarized. That is incorrect. The amplitude of a wave is directly proportional to energy transferred by the wave. Well, no, because I is proportional to A squared, so not true. And intensity is related to energy, because it's power. The frequency of infrared light is greater than the frequency of ultraviolet. No, it's the other way around. The frequency of infrared light is less than the frequency of ultraviolet light. So our answer is A. For this one, you need to remind yourself what a stationary or standing wave looks like. Remember, it goes from node to antinode to node, but one whole wavelength represents all of this. So going node, antinode, node, antinode, node. So here we're going from a node would be when the intensity is 0, to an antinode to a node. So that distance there, which is 10 centimeters, or 0.1 meters, corresponds to half a wavelength. It's effectively this distance here to here. So 0.1 times 2 gives me 0.2 meters as my wavelength. Frequency equals V over lambda. Equation loves to come up. So 340 divided by the wavelength, that gives you 1,700, so your answer is A. Which statement about longitudinal waves is correct? So only one of these. Longitudinal waves include radio waves. No, they're trying to trick you there because you think sound is carried on radio waves. Radio waves are electromagnetic. Particles of longitudinal waves vibrate at right angles to the direction of travel. Nope, they parallel to. That's describing transverse waves. Nope, no waves can be polarized. So the last one must be true. Stationary waves can be produced by the superposition of longitudinal waves. Yes, I mean the last question gives you a clue to that. The order of magnitude of a frequency of the longest wavelength ultraviolet light. Now, you either know this or you don't. Again, if you don't know it, check your answer. Check your notes. It's B. Now, remember, you will have learned the wavelengths for all of these. So you need to use the equation V equals F lambda to find possible frequencies. Remembering that the speed is 3 times 10 to the 8 over the wavelength ranges that you know. That will give you an answer. Only one possible is B. Question 16. Now the student measures the wavelength lambda and the frequency f for these waves. Now you notice that lambda's already in here, that's great, but we don't have f. So we need to get f into that equation. Now g, 2 pi and 2 and pi are all constants, so we don't need to play with those, but v is a variable. We need to remove that because it's not one that's being measured or changed. So we need to put in for f. So substitute in v equals f lambda into this equation. You get f lambda squared equals g lambda over 2 pi. Expand the brackets, f squared lambda squared equals g lambda over 2 pi. Take the lambda over to the other side. So it'll end up being down the bottom here. And then you'll see that the lambda on the top cancels with the one on the bottom to leave you with g over 2 pi lambda. So what do we need to plot to get a straight line? Well, remember, we're going to have to plot, we're going to have to get the form y equals mx plus c. So what we can plot on the y-axis is f squared, so it's one of these two. And on the x-axis, we're going to plot 1 over lambda. So this is our answer D. This here will be the constant that we'll get, the gradient, which is constant. What two significants are the period and frequency and the amplitude of the wave represented here? So lots to get. Start with amplitude. Amplitude is the maximum displacement from the equilibrium position. So 5, 6, just below 7. So we're looking at either that one or that one. These are double, so trying to see if you think that's the amplitude, which it isn't. This is the amplitude. Period, well, that's one complete oscillation, so we'll start from 0 and go to there. So that's 3, and then it's going to be about 3.4, 3.5 times 10 to the minus 3, so that gives us the only option, which is C there. 2.7 is if you think this goes, and you think this one's 3 here, you'd go for 2.7, so a bit of a trap. This one has two waves, it shows their pressure variations, but effectively it's just a sound wave represented on here. Think of it almost as displacement, but it isn't. And the key thing is, the bigger the pressure variation, the bigger the change in the amplitude, because it asks the intensity of wave 2 given intensity of wave 1. The first thing you'll spot that wave 2 is a bigger amplitude, so it's going to have a bigger intensity, so we're looking for a bigger answer. They're all bigger, so that doesn't really help us at this stage. And the key equation we're going to be using is I is proportional to a squared. You'll notice that from wave 1 to wave 2, we go up by a factor, we go from an amplitude of 2 to 3, which is a factor of 1.5. So that's the change in amplitude. So if that goes up by a factor of 1.5, intensity is going to go up by a factor of 1.5 squared. So if we times that by 1.5 squared, we'll get 3.6 times 10 to the minus 6, and that's our answer there. The diagram shows the vertical cross-section of waterways. At which point is the water moving upwards with a maximum speed? Now remember, this wave is moving this way. So you look behind it, you look to the left of each point to see what's coming next. So for point A, this is coming next, so it's moving down. Point B is at the top and is about to move down as well, so it's neither A or B. Point C is going to start moving up in a moment, but D is also. So which one's moving faster? Well, you can look at the kind of the gradient of the line coming. You can see that C is going to be faster. Or think about it, this has just stopped and is about to start accelerating upwards, where C's already accelerated this whole distance, so therefore C is your answer to this. It will be going upwards at the maximum speed. Key thing to learn from this is remember to look behind each point to see what's coming next. This one again, you either know it or you don't. If you don't, check your notes. C. Which statement about light waves and sound waves is correct? Both can be polarized. Nope, sound can't be. Both can travel through free space. No, I assume they're referring to a vacuum there, but we'll look back at that one in a second. Both have a frequency inversely proportional to the wavelength. That's true. If V equals F lambda. Both have an intensity proportional to the amplitude. No. If it said squared, yes, but no. The answer is C for that one. Question 22. This is looking at polarized light, and it's going through a filter as shown. And it's emerging with A cosine theta on the other side. What is the intensity of the emerging light when theta is 60? Well, first of all, we can work out what the amplitude is and then square it, or we can just use Malus' law, which we hopefully remember, I equals I naught cosine squared theta. So the initial intensity is I, which really, is I naught in our equation. Remember, this is the initial one, and this is the one on the other side of the filter. So intensity of emerging light when theta is 60, so that's 60 relative to the plane of polarization, so that's what goes in our equation. So basically we're looking for cosine squared, cosine 60 squared, which gives us 0.25, so our answer must be A. So electromagnetic waves from an unknown source in space were found to significantly diffract when passing through a gap of the order 10 to the minus 5. What type of wave could this be? Well, this is relying on realizing that diffraction is best when the wavelength matches the gap size. So if this is x, the gap size, it is approximately equal to the wavelength. So for this one, we think what has a similar wavelength to 10 to the minus 5, and that is infrared. This graph shows the height, how the height of water surface at a point in a harbour varies with time t. The wave passes the point. What are P and Q? Now, first of all, you check your axes. This is height. Now, P over here will be the displacement. So it's not the amplitude, because the amplitude is the maximum displacement from the equilibrium position, but it's not in this case, that P. Q, well, we look at our axes, is it wavelength or time? Well, if this was distance, it would be wavelength, but it's time. So Q represents a time period. So the answer 24 is A. 25, what is the period of this wave? Well, this is nice and easy. T equals 1 over F. Just remember, giga is 5 times 10 to the 9. 1 divided by 5 times 10 to the 9 gives us 2 times 10 to the minus 10. Now it's deciding which one's the right one. Now, you might remember, but you can check all of them, nanos times 10 to the minus 9, nanos times 10 to the minus 9 there, so it's neither of those two. But pico is times 10 to the minus 12, so if you knock that back 2, that's 2 times 10 to the minus 10, so 25 is D. 26. Question 26. So you have light of amplitude A shining on the surface of area P. Now we're going to 2A, and we're going to an area, not area P, area S. Now we're going to a third of S, so smaller area. So we're going to expect the intensity, or the power per unit area, that's just intensity, seeing if you know your definition. Power per unit area is intensity, is going to be more. First of all, what happens with the amplitude? Well, remember that intensity is proportional to amplitude squared. So if we double the amplitude, we're going to have 4 times the intensity. So 4 times the power P, or the intensity I, depending on which one you use, but they're referring to it as P, so 4P. And it's on an area a third of the size. So that means we're going to actually end up with intensity of 3 times the amount, or 4 divided by a third. Why? Because intensity is the power per unit area. So if the area is reduced by a factor of a third, well, you divide it by a third. 4 divided by a third is going to give me 12, which gives me C. So we have a wave of speed 340 in a period of 0.28. I'll just explain how you're going to go over it, and you can do the rest of it. It's pretty simple. You can work out the frequency using 1 over T. Just be careful, it's milli, times 10 to the minus 3. And then you can use lambda equals V over F to get your answer. 28. Which line in the table summarises the change in wave characteristics of going from infrared to ultraviolet? Now you might remember ultraviolet's got more energy, that's why it can damage your skin, so the frequency is going to be increasing, so it's one of these two. And the speed in a vacuum, well, it's the same for all electromagnetic waves, it's going to remain constant, so the answer is C. So this one refers to visible light. Now hopefully you remember that visible light goes from 400 nanometers, which is blue, to 700 nanometers approximately for red. That's the visible light range. So the order of magnitude of the shortest wavelength of visible light, shortest wavelength is blue, so 400 nanometers. Frequency is equal to V over lambda. And obviously it's an electromagnetic wave, so it's 3 times 10 to the 8, divided by 400 times 10 to the minus 9. Type into your calculator. And you get 7.5 times 10 to the 14, so the answer is C. Got two waves x and y. Wave x has an amplitude of 8 and a frequency of 100 hertz. What is the amplitude and frequency of wave y? Now, for amplitude, we're looking roughly how much it's changed by. Let's start with frequency so we can round some down. So here's one oscillation for wave x. Within that, we've got 1, 2, got 2.5 oscillations for wave y. So it's going to have a frequency of approximately 2.5 times. We've got 2.5 times number of waves in there. That's a rough one. I've obviously slightly miscounted here. So going 1, 2, sorry, I miscounted, it's 3. So you can see there's 3 oscillations within 1 there. So they're 3 times 100, so we know it's 300. Now, which is the correct amplitude? Well, it looks like to me it's about half of 8, therefore 4, so the answer would be D. Question 31, what is correct for all transverse waves? Well, they are all electromagnetic. That's not true because water waves aren't electromagnetic. They can all be polarized. That is true. That's true of transverse waves because they oscillate in 90 degrees to the direction of travel. They can be polarized. They can all travel through a vacuum. No, I'd like to see water traveling without any water particles. Remember, a vacuum has no particles, so that's not possible. And they all involve the oscillations of atoms. Well, you know that electromagnetic waves don't. They're oscillations in the electric and magnetic field. I'm now going to focus on the hardest questions of the remainder of them because they do get a bit repetitive. 35 is a bit unusual, about an LCD or liquid crystal display, which is used on some phones and so on. The display changes when the polarizing filter is rotated. So that means the light coming out of it is polarized. Now that's not an option. We've got unpolarized there, but that's not right. It's definitely polarized. Now we know if it's polarized, that it can't be a longitudinal wave. So it must be a transverse wave. So we know the answer is C. This, well, we don't know. We don't have a clue. There's no information to tell us whether that's true or not. Question 37 is quite difficult. So we've got a displacement time graph and we're told that the intensity is halved. So we're asked for which is the new graph. Well, we can work that out by thinking about the amplitude. And the amplitude here is 4 blocks. I mean, we can rule out some. You can see A is definitely gone because it's a different wavelength and it's meant to be the same one. Intensity is not going to change the wavelength of it. But that doesn't help us with B, C or D. And the best way to think about this is I is proportional to A squared. And therefore we know that A, if we square root both sides, is going to be proportional to the square root of I. We know from the question that the intensity is halved. So this goes down by a factor of a half. Well, because it's proportional to the square root of I, we know that this is going to go down by a factor of 1 over 2 square rooted. Or square root of 1 is 1, so it's just 1 over root 2. Or if you think about it another way, you've just got to go down 4 divided by root 2, or 4 over root 2 is going to be the change. If you work that out, just type into calculator, you get 2.8. So that tells us that D must be the answer because that's 2.8 squares if you look at that. Going down, just to note that you can skip question 40. If you had to go, great, but we haven't done standing waves fully yet, so that one can be skipped. 41. His meter reads I. It corresponds to an amplitude of A of the sound wave. At another position, the meter gives an intensity of 2I. What is the corresponding amplitude of the sound wave? Remember, this is the idea that I is proportional to A squared. But we want to look at amplitude now, so we'll realise it's proportional to the square root of I. So if I goes up by a factor of 2, well, A is going to go up by a factor of the square root of 2. So the answer in this case would be B. That's all the hard questions I'd say in that paper. But if you've got any other questions, just let me know and I can help with those. Well done.